Yes. Hello. Welcome everyone to the day 2 of the EPS-SG Radio Occultation Mission webinar. I am Srireka Thoniparambil. I manage the EPS-SG user preparation project at EUMETSAT. For those of you who were here yesterday, welcome back to today's session. As you know that we are organizing this webinar in 2 days, and today is day 2. And for those who are joining only for today, let me try to give you a short introduction to this webinar series. So together with Stefan Budzinski, my colleague here in EUMETSAT, who is the MTG User Preparation Manager, we are organizing this next generation user preparation webinar series to cover all the observation missions that are part of our polar and geostationary mandatory satellite programs. So this is MTG and EPS-SG. And we are aiming to give you an overview of all the missions, basically trying to cover the measurement techniques, scan geometries, channel specifications, the generation of level 1B and level 2 products, their details, their formats, then dissemination, and also some application perspectives. So what we did yesterday was Christian Marquardt, he gave a nice introduction to the radio occultation. So we are now, we have done most of the missions on board MTG and EPS-SG, except this Copernicus Sentinel-4 and Sentinel-5 missions. And so now we are at the radio occultation on board EPS-SG satellites, METOP-SG A and B. Yesterday, Christian Marquardt, he gave a nice introduction to the RO measurement technique, and then Ricardo Nota-Petro, he gave he gave a detailed information on the RO mission that's part of METOP-SG A and B. He also gave a nice introduction to the products and their formats and how they will be disseminated, and also information on the test data. Then we had Ian Culverwell from Met Office on behalf of the ROMSAF. He gave a presentation on the radio occultation radio occultation processing package, ROPP. So today we nicely glide into the next topic, the application perspectives for RO data. And today we have 3 presentations, Sean Healy and from ECMWF and Axel von Engelen, EUMETSAT. They will give a presentation on the application of RO data in NWP. Then Hans Gleisner, he will give a talk on the application. He's from Danish Meteorological Institute and will give a talk on the applications of RO data in climate, and a talk on space weather applications by Ricardo Nota-Petro, EUMETSAT, and Manuel Hernandez Pajeros, Universitat Politécnica de Catalunya. So that's how we are going about today. I welcome all of you to this session, and I would like to remind you that, like yesterday, we would use Slido tool for asking questions. You will have in the chat how to access Slido and how to ask your questions. It's pretty much straightforward. You type in your questions and we will take up your questions during the Q&A time. So after each talk, there's about 10 minutes for questions, and I will read out the questions and the panelists would answer these questions. We will have 2 short breaks as well. And during, what did I want to say? And one thing I wanted to say is that we will make available all the recordings and the presentations and also the Q&A sheets. So with that, I welcome Sean Healy for this presentation on the application of RO data in NWP. Sean?
Very much. Hopefully you can hear me.
Yes.
I'm going to share my screen and we will go from there. So
yes, Sean, that super. Looks good. Yeah.
That is a good start. So thank you very much for this opportunity. So we're going to talk about the application of level 1B data and level 2 data in numerical weather prediction applications. It's a joint talk by myself and Axel. I should say I'm based at the European Centre. Axel is obviously EUMETSAT. And I've worked as part of the ROM staff now for a very long time. And so we'd like to acknowledge all of those bodies. And I'd also like to acknowledge Niels Borman, who's really provided some really exciting new results that I'm going to present today. Thank you to Niels. So a brief outline of what I'm going to try and cover. I'm just going to show a slide early on to show you how the number of satellite data we've had available for NWP applications has evolved since the 1990s. And you can see that from that slide, we actually have quite a lot of data that's available for us. Then I'll recap a little bit about the GPS or GNSS-RO geometry. This is one of the problems of being in this subject for a long time. You have to get used to calling it GNSS-RO rather than GPS-RO, which it was for a long time. So I'm going to talk about the geometry and information content briefly, recapping essentially what Christian covered yesterday. And then I'll go into giving an overview of some recent observing system experiments that Niels Borman provided. And that gives you an indication of where occultation and red occultation data is having an impact in NWP systems. I'll say a few words about what's called a forecast sensitivity to observation impact, which is a globally integrated measure of impact on forecast skill that we use quite a lot in numerical weather prediction. And then we'll move over to Axel, who's going to talk about the use of level 2 data in NWP applications. Then, if it all goes smoothly, it'll be back to me to just summarize a few points. So this is a time series from the mid-90s, 1996, which coincidentally is the proof of concept for radio occultation, 1996. And it shows the number of sensors, satellite sensors that we have, we're monitoring currently at ECMWF. And you can see how it's evolved and increased with time. And just around about now, we're talking about at least, well, around about 100 sensors that go into our operational NWP applications, either for monitoring or active assimilation. So we have a lot of satellite data that's available for NWP application. And the key thing is that you have to recognize, and you've probably got this if you've been to other aspects of the webinars, the different components of the satellites have different strengths and weaknesses. So for instance, if you want to understand wind speed or wind vector information near the surface of the ocean, you look for a scatterometer, whereas if you want to understand the temperature information in the stratosphere, upper troposphere and stratosphere, radio occultation is more what you're going to look for. But the key point is that we need a balanced observing system, which takes into account the different strengths and weaknesses of all the data sets that we get. And then when you get a new data set, or you look at a data set, you have to ask yourself, what does it really bring to the global observing system, the data we already have, that wasn't there before? Because information content is relative. It really depends on what you already know. There's not much point focusing on a satellite system that already tells you measure something that's already measured if something else is not measured in your system. So that's what the background. So the question then for radio occultation is, what does it bring to our global observing system that's and for NWP applications that other systems perhaps don't do quite a good job on? I'm going to go back to the GNSS-RO geometry that Christian showed yesterday, and it really gives you an indication of and a hint of what radio occultation really does. Now, as Christian pointed out, essentially we're looking at a ray from a GNSS satellite passing through the ionosphere and neutral atmosphere. And after some pre-processing, a lot of pre-processing, we obtain the bending angle, alpha in this particular plot, as a function of this height variable, which is called the impact parameter. So if everything is spherically symmetric, these two parameters, AG and AL, are actually the same. So we obtain bending angle as a function of impact parameter. Now, bending angle is related, as Christian showed, to the refractive index gradients in the atmosphere. And we are able to extract that information about the atmospheric state from the bending angle information directly. And that's what most NWP centers currently do. So we retrieve the bending angles as a function of impact parameters. So we have bending angles as a function of height. And as I said, that provides us the information on the atmospheric state that we're actually interested in. We want to understand or get a better estimate of the temperature profile information or humidity profile information from having access to these bending angle profiles. So we have to have a forward model that computes from our atmospheric state, so our temperatures, our humidities and pressures. We give it to our forward model, and the forward model will compute the bending angles as a function of impact parameter as part of our NWP system. Now, the key characteristics of radial occultation that really make it a useful contribution to the global observing system, and it has a number of useful properties, but I always think that probably the two key properties that kind of stand out is that it can be assimilated, or it can be used in our NWP system without bias correction to an NWP model, which is very useful for estimating and correcting biases in short-range forecasts or model biases and so on. And it also, because of the limb geometry of the measurement technique, provides very good vertical resolution information with very good vertical resolution. But because it's limb sounded, the horizontal resolution is not as good. The information is kind of averaged over a few hundred kilometers, but the vertical resolution is extremely good, and that's what complements the other observing systems that we have available for data assimilation. So, for instance, if you assimilate radiances, they have quite poor vertical resolution, but very good horizontal sampling. We have the complementary situation, and that's really the basis of why radial occultation kind of is a useful contribution, because it tells you something different to what you already know. What we do within an NWP system, as I've said, is we use this kind of forward model. Now, the way I think about data assimilation, which is what the process of where we try and merge an observation with a previous forecast, is essentially it's a huge least squares fit problem. So what we try to do is to take the bending angles and we try and find an atmospheric state that will fit our bending angles in bending angle space to within their error characteristics, and at the same time be consistent with a short range forecast to within its error characteristics, and by minimizing this cost function. And then what we do here is we will have a set of data points that vary in a time window. In this particular plot, the time window is between 12-hour window between 3 in the morning and 3 in the afternoon. And we try and find the model trajectory that will fit the observations throughout this time window. So the model, the NWP model as such, in temperature and humidity space, is used to interpolate the observation time and location. And then we compute the bending angle with what we call the forward operator. And that's what Ian was talking about yesterday in the context of ROPP. We have these bending angle forward operators that allow us to go from state space, which is temperature, humidity, pressure, and so on, into bending angle space. And that's what we do our least squares fit in. So we try and fit the bending angles to within their error characteristics, and at the same time fit the previous forecast to within its error characteristics. Now, the radial occultation data has quite interesting properties, and I think this monitoring plot that I kind of downloaded today from the ROMSAF monitoring pages is quite interesting because it shows you where we expect to see the biggest impact from radial occultation. This particular plot shows the departure, the difference between the observed bending angle and the forward model bending angle from a short range forecast. And we've normalized it by the short range forecast value. So it's what we call O minus B over B. And you can see that the percentage difference between the short range forecast and the observations is lowest in this region from around about 10 kilometers up to about 35 kilometers. And then it starts to increase above that, and it also increases below that. The measurements are harder to make in the lower troposphere. You have a lot of signal dynamics, and that's why we have horizontal gradient errors going on in there as well, and that's why the departures tend to get bigger as you move towards the surface. As you go higher up, we have additional errors caused by residual ionospheric problems and so on. But this kind of region here, between around about, it's not precisely defined, about 10 kilometers and 35 kilometers is where we give radio occultation the most weight in our NWP systems. And that's where traditionally we've seen the biggest impact from radio occultation data today. So what I'm going to do now is just really go through some results that were produced by Niels Bohrmann very recently and presented at the annual seminar at ECMWF. Now, when you have these different observing systems going into an NWP system, what you'd like to do occasionally is pull them out and see what impact is in the forecast. Obviously, if you pull out your radio occultation data, what you hope to see is the forecast errors go up because it's no longer there. So Niels has done a really interesting set of experiments. They're called observing system experiments, OSSEs for short, where he's pulled out different components of the global observing system from our NWP system and seen how the forecast errors get bigger in a statistical sense when these are removed. So the first thing he's done is remove all the conventional in situ observations for radiosonde, surface pressure observations, and so on, data like that. Microwave radiances, he's pulled those out independently. So the AMSU radiances and so on, they've been removed. IR radiances from LEO satellites, ERZ, CRIS, and so on. And also the GNSS RO data. And what he's then done is compare where the impact is from these different observing systems. And this has been really a really nice set of results. And I'm going to show you initially some short-range forecast apart. So as I said, as you remove this data that's in the system, you hope to see the errors get bigger. And this is what I'll try and explain it in this in some detail in this particular plot. This shows, if you look on the left-hand side, this shows the globally average temperature departures. So how well a short-range forecast fits radiosonde information when different observing systems are removed. So if you look at the radio occultation data, when we remove it from our NWP system, all of a sudden our forecasts get worse and we no longer, our short-range forecasts no longer fit the radiosondes quite as well as they did. And you can see the blue line, which is the radio occultation data for the temperature, it's around about 2% degradation in the radiosonde fits from about 300 hectopascals. It increases a bit above that. And then you can look at where the other observing systems are having an impact. So you can see the microwave, you see the RO is really having the biggest impact above 300 hectopascals, and it's actually bigger than the observing systems. But then you see the microwave data is having a bigger impact at 400 hectopascals than the RO, and similarly the IR is having a bigger impact than RO below 400 hectopascals. You can do the same thing if you look at wind measurements. That's the middle panel here, and again you can see that the RO is having the biggest impact above 200 hectopascals in the wind. Now, as I said, this is this kind of interval above 200 hectopascal is the core region. That's where we expect to see the RO having the biggest impact, so that wasn't a big surprise. But the nice result that we're starting to see now in these short range, in these particular OSSEs, is also an impact on tropospheric humidities that's always should have been there in theory, but it's been quite difficult to actually establish in fact. So if you look in the blue line here, on the right-hand side, you can see that our ability to, our short-range forecasts no longer fit the radiosonde humidity information in the troposphere once radio occultation has been removed from the system. You can also see that the microwaves are having a bigger impact in the troposphere on the humidities than the RO, but nevertheless, it's a very promising result that we can see. Now, these are short-range forecast departures, so these are around about 12-hour forecasts, but we can generalize these results to look at the forecast, the impact of the different observing systems out to day 8 or day 10, and I'm going to show you a summary of some results from that like that now. Now, this is the forecast impact for the different systems looking at wind vectors at 200 hectopascals. So you're talking about wind at about 10 kilometers at 10 kilometers altitude. The blue lines are how the wind errors, the wind error statistics increase when radio occultation is moved from the system. Southern hemisphere is on the left-hand side, tropics in the middle, and northern hemisphere on the right-hand side. In particular, if you look at the southern hemisphere, you can see that RO at 200 hectopascal is having quite a significant impact on the wind vector errors. And this impact is statistically significant, certainly to about day 4, marginal at day 6, and not quite statistically significant at day 8. But you can see it's a fairly decent impact. We also see a good impact in these wind vectors, 200 hectopascals in the tropics. Not such a big impact in the northern hemisphere, which I presume is because we've got much better conventional data. You see the light blue is the conventional data impact in the northern hemisphere, which is bigger in the northern hemisphere than in the southern hemisphere because of the availability of observations. But you can see that RO is clearly having a significant impact on the vector wind errors at 200 hectopascals. We look at 850 hectopascals, which is close to the surface, of course, about 1.5 kilometers above the surface. We're still seeing an impact. Largest impact we're seeing is in the tropics in this particular parameter. Not such a big impact in the northern hemisphere, but certainly the tropics is a nice result, and it probably is related to the fact that we had this big increase in Cosmic 2 data that went into our operational system in 2020, in March 2020. We can look at other variables, and this is a really key one that I think has been a long time to really establish. This is the errors in total column water vapor in the different regions, southern hemisphere, tropics, and northern hemisphere. And for instance, in the tropics, you can see we have a statistically significant impact in the total column water flow forecast out to day 8. Smaller impact in the northern hemisphere, bigger in the southern hemisphere, the northern, but the tropics is really quite an interesting result. And as I said, I think that's the kind of new result we've achieved over the last few years is an impact on water vapor. Z500 is a traditional metric that we use quite a lot in NWP. Southern hemisphere, we're not having as big an impact as the microwave sounders in these particular experiments on the Z500. Comparable to the IR, LEO IR in the southern hemisphere, but you'd say the LEO IR is probably having a bigger impact in the northern hemisphere. But the microwaves and conventional data are clearly most important in the northern hemisphere. So, no, overall, I mean, I think if we'd looked at more stratospheric parameters here rather than the kind of 200 and below parameters, we would have probably seen RO having a bigger impact than some of the other observing systems. But I think this is really a really positive step with the latest RO data. And as I said, what we're doing with the data is ingesting it as bending angles in bending angle space. One more parameter that we use to look at the impact of the various observing systems is something we call the forecast sensitivity to observation impact. This is quite a complicated quantity, but essentially it's a globally integrated measure of the 24-hour forecast errors. So we look at some kind of weighted average of temperature, wind, surface pressure forecast errors, and 24-hour forecast errors, and look to see what contribution the various observing systems make to the reduction of these forecast errors. And so it's a busy plot, but I'll highlight the thick orangey line, which is the RO impact, and by this particular measure, that at the start of 2020 was about 4%, and then it increased to around 10% when Cosmic 2 data was available in our system. And when we had this period, which was trying to mitigate the loss of aircraft data, you'll notice the kind of turquoisey light blue line is the aircraft data impact in our system, where we lost a lot of aircraft data last year because of COVID. We put Spire data in for a period from May to the end of September, and that increased our impact by this measure from about 10% to about 13-14%, and then it reverted back to 10% after that when the data was removed. You can also see other data sets. But I think the key point I'm trying to make here is that the RO is certainly in the mix now. It's having a decent impact on various measures, and the big new result probably is the impact on humidity. I would say the impact on stratospheric temperatures, uptropospheric and stratospheric temperatures have been established for quite some time, but I think the new tropospheric humidity scores are really quite new and exciting. So that's a kind of a whistle-stop tour through the bending angle assimilation. And I'm going to carry on sharing the screen, but Axel's going to talk through the next few slides about how we also use the data in refractivity information in NWP systems. Okay, Axel?
Yeah, thanks, Sean. So I'm going to go through level 2. Sean's giving a nice introduction into the level 1. Level 1 is the key characteristics that he mentioned are of course also mapping through to several of the level 2 parameters. So the high vertical resolution, the bias-free observations. And level 2 is also a bit closer to like atmospheric parameters we know about. Bending angle is always something a bit more difficult to explain, as you've seen in several of the plots that have been shown. So next slide, please. So here's a list of the EUMETSAT ROMSAF level 2 NWP products. Reminder in the first line. So the products are provided by the ROMSAF. Timeliness is better than in the EPS system, 2.5 hours and down to 125 minutes for regional data. The prime product that comes from the 1B processing to level 2 is the refractivity profile. That's been around for a long time. Other profiles that the ROMSAF provides are temperature, pressure, and there's also a dry temperature profile. So one of the temperature profile is using a priori information, so something similar what Sean just showed in a 4D var, but only in a 1D var. So you get specific humidity profiles and temperature profiles out by combining the observation with background information. The dry temperature profile on the other side doesn't use that one. There's also a surface pressure available, tropopause height, planetary boundary layer height. Some of those were already introduced yesterday also by Ian in his RPP talk. So next slide, please. If we look at the global NWP users for refractivity, it's not such a big user base as we have for the bending angle. So there's Environment Canada, who actually use an advanced uncertainty characteristics and assimilate refractivity data, and have found that to be better than the bending angle assimilation, primarily because they use this advanced uncertainty measure on when they assimilate the data. So technically, we think that the bending angle should provide more information, but in some cases, as I said, for Environment Canada, it is better for them, it's giving better results to work with refractivity. There's also some NWP centers like Météo France who use the data for quality control because it's easier to estimate refractivity and then to calculate a bending angle profile. Moving on to regional NWP users. So there aren't that many systems that operationally assimilate that data. So it's primarily study application. We've seen a lot where they looked at hurricane typhoon forecast improvements over, for example, over Taiwan, because the cosmic and cosmic 2 constellations are greatly supported by Taiwan. And those ones have or are expected to have more or getting more attention with the daily numbers that will become available, well, already now and in the future, as you see now. Sean has shown the Cosmic 2, which provides several thousand occultations per day, and there's also the Spire. There are other observing system, EPS-SG, then in a few years from now. So all these will, of course, provide you more data in your smaller regional NWP model. The other application for refractivity in NWP, regional NWP, is to use it as an alternative to the more complex bending angle operator, especially if the model has a lower top altitude. The operators themselves are all available in the ROPP. So the ROPP has really nice bending angle and refractivity operators, everything you need to know or need to have for assimilation into an NWP model. But if the upper top of your model is only at 30 kilometers, you might be better off with using refractivity data. And that, as I said, once you have more data, should also become of more interest. There is another application where you could, which you could call like real-time climate application and monitoring. Some of that is happening at the ROMSAF, so they do generate interim climate data records. In those, you have to make sure that the processing is actually consistent. So you shouldn't introduce processing changes, but otherwise you can then kind of get a good glimpse at how the atmosphere is reacting on short scales, and you don't have to wait for a reanalysis run or something like that. There are some other applications. So we also at EUMETSAT and other colleagues of us have started to look at using temperature profiles and forward modeling them to brightness temperature, and then you can monitor microwave instruments which are known to have biases. So you can actually check instrument issues in near real time by doing that. Others that I am aware of is that some chemistry model actually use also NRT temperature profiles. I've seen that they use SABRE or other models, especially if they want to constrain the upper stratospheric temperature and get their near real time information. That actually concludes my level 2 part. So I pass over to Sean with the summary.
Thank you, Axel. So yeah, I don't want to cover this much more. We've tried to give a brief recap of the measurement technique that Christian went through in detail, and shown some current impact experiments using bending angle in the ECMWF system. The point I would make is the RO has a very big impact on upper troposphere and stratospheric temperatures. That was always expected. It's well established. We have quite a big impact on tropical winds. It's probably not quite as, it's more of a surprise maybe, because some of the balance conditions are not so obvious there. But I think the key thing is that we're now seeing impact on total column water vapors. So we are actually exploiting the data pretty well in the troposphere as well. Level 2 products, as Axel said, there are some users who are assimilating refractivity into their global NWP systems, other users who use the refractivity information as QC, and the use of refractivity in regional models, in particular when the lid is a bit lower. So that's about it. Thank you.
Thanks, Sean and Axel. I think we have we can take up a few questions at least, because we're a bit in short of time.
Sorry about that.
Let me just bring up the questions actually. So that's for you, Sean. How many occultations roughly go into one assimilation window?
Yeah, that's a good question. That's changed a lot over recent years. Since we got Cosmic 2, we're getting around about 5,000 Cosmic 2 data occultations per day. So you're talking about 2,500 of those in a 12-hour window. But we also get 1,800 GRASS measurements from the 3 METOPs, and then other lower numbers from FY3D. So you're talking probably around about 8,000 profiles per day, okay, currently, and maybe some more from Spire that's just coming into our system.
Okay. Mm-hmm. What are the stratospheric parameters that you can use as a metric for measuring the impact?
Well, we look to see in the stratosphere as to how well we're improving the stratospheric temperatures and wind information. We don't see the humidity there because we're not sensitive to that. But you can see, certainly when we put Cosmic 2 in, you could see impacts on stratospheric temperatures and winds out to, you know, day 5, day 6 and stuff. So you look to see how well the forecast of winds and temperatures are improved.
Okay.
Spire, I can see the Spire question.
Yes, this one Spire question. Why was the Spire data taken out after 2020 September?
Well, it was no longer made available. Spire very kindly made the data available as a kind of mitigation for the loss of aircraft data.
Okay.
And they made this available for from April until the end of September. But now, as we're starting to look at Spire again, so it could be going back in quite soon.
Okay, good. I think we are just keeping the time actually very good. So you didn't do anything there, so we can still go for a break of 5 minutes actually. So we will meet again in 5 minutes. Take a break, please. You may want to bring up your slides. I mean, we start in a minute, but you can already put your slide up. Actually.
Okay. So let's see here. Should I share my screen already now? Do you think?
You can put your title slide up. I mean, yeah.
Right.
And actually, we can start because it's 14:40 now, so
Yes.
we are in time.
So there it is.
Yes, yes, we can
Right.
see everything clearly.
Yes.
Please start, Hans. Thank you.
Let's see. Okay, so I'll start then.
Yep, please.
Yes. My name is Hans Gleisner. I work at DMI in Copenhagen, and we're a few colleagues at DMI, and together with other colleagues at ECMWF and Met Office and IEEC in Spain, we work within EUMETSAT ROMSAF team to process our data and also to generate climate data records, and that's the topic of this talk. So I will add something about characteristics of our data that are particularly important for climate. We heard, for those of you who listened in yesterday, we heard some details about how our data, what are their main characteristics, and also Sean's talk today gave some important information on that. But I will just point out a few issues that are important for climate. But then I will mainly go through a few examples of how our data are used in climate. It is by no means it's not a complete set of applications. It's just what I have been slightly involved in and know about. And then I will conclude and show you where to find data. So sampling is an important issue, and of course RO instruments, they are carried by these polar orbiting satellites. So it's so much of the sampling characteristics they share it with other type of instruments also. But there are some particular characteristics, and that is one thing is that it's sort of quasi-random spatial distribution in latitude and longitude, and that is because it is a limb sounding instrument, and we get an observation in the direction of a GPS satellite or a GNSS satellite, and it's of course in reality it's not random, but it's sort of quasi-random distribution. It looks random. It's also independent of clouds because it's a microwave instrument, and it's independent of the underlying surface. There are no dependencies on surface emissivity and things like that, and also no land-sea differences. These characteristics makes it a truly sort of global observing system. And let's see here. So with a single satellite tracking, say, one GNSS system, GPS system, both rising and setting occultations, we get around 700 occultations. It's perhaps down to 600, 650 occultations per day after quality control and rejection of a certain percentage of profiles, but roughly something like 20,000 occultations per month from a single satellite. And so that is the case for the METOP satellites. In the case of EPS-SG, there will be first we have METOP-SG A and B, so they go in pairs. So that's a factor of 2 more, and METOP-SG will also observe other GNSS satellites than GPS. So they will observe Galileo signals, which adds another factor of 2, and there will also be some observations of the Beidou system, which adds another percentage. Ricardo mentioned 50% additional yesterday. But this means that let's say METOP-SG A and B will perhaps be around 100,000 occultations per month, distributed across the Earth like this. So we have this distribution in latitude and longitude. It's mainly governed by the satellite orbits, mainly by the inclination. Both METOP and METOP-SG are sun-synchronous, are in sun-synchronous orbits, which means that they go very close to the pole. So there is a variation with latitude, with a denser number occultation numbers toward the poles, as we can see here in the panel to the left. In longitude, there is almost roughly uniform distribution, at least if you observe over long enough times, let's say over a month or so. So as I said, it's sun-synchronous orbit. So that's the normal for these operational weather satellites. They observe at one particular local time. They cross the equator at one particular local time. In the case of METOP and METOP-SG, that is 9:30 in the morning and 9:30 in the evening when they cross the equator, which means that only parts of the diurnal cycle are actually observed by these satellite systems. But we have our instruments on board other systems like Cosmic 2, CHAMP, GRACE, other satellite RO missions, which are very important to fill out the gaps in local time. Then we also have another characteristic, and that is that they are these data, our data are they are sort of long-term stable. They have an intrinsic stability which many other observation types don't have. MSU instruments, for example, and many other instruments that observe radiances, they rely on intercalibration between missions and instruments to be able to form long time series. But in the case of RO, there is an expectation that we can actually put them together, data from many different satellites, and they will actually work as a continuous time series. And that is also the case, at least in a certain in this core region of the atmosphere that Sean talked about. So there is an excellent consistency between missions, perhaps let's say from the middle troposphere up to the middle upper stratosphere, something like that. Roughly 8 to 30 kilometers in dry temperature. We can form long time series. In reflectivity and in bending angle, we can go higher up. Bending angle, we can probably go above 40 kilometers and form these long time series, which we can use to compute trends and so on. There are slightly larger biases down in the lower part of the troposphere, which are still a sort of area under development, trying to sort out these biases. All right, so now we'll go through a few examples of our use of our data in climate applications, and I will start with something related to what Sean talked about, reanalysis, assimilation into reanalysis systems. This plot shows 100 hectopascal temperatures in the tropics from 5 global reanalysis. All of them, the colored lines here, assimilate our data except the gray line, MERA. But they didn't start assimilate our data until 2006. That's here. And what we can see is that the colored lines, they actually converge quite nicely at the very point where our data started to be assimilated. It's so reanalysis. In reanalysis, we have this very strong, important impact of RO, similar to what Sean talked about in NWP systems. Okay, but so reanalysis, RO for reanalysis is an important applications in climate. But we also do monitoring, pure monitoring. In the EUMETSAT ROMSAF, we compute long time series from not just from the EUMETSAT missions, but also from other missions. And so here's an example of gridded monthly means of bending angle, reflectivity, and dry temperature, and geopotential heights. Geopotential height is a very useful quantity, actually, which I will show some examples of. We also compute monthly mean humidity, only up to 12 kilometer though. It's that's higher up than that. There are not really any humidity information in the RO measurements. And we also compute things like tropopause heights and other derived variables. So this is these plots show tropospheric humidity. So as I said, up to 12 kilometer. So it's zonal grids here, latitude against height, specific humidity. In the middle panel, shows standard deviations, and to the right here we show something we call a priori fraction. It's a sort of a quantification of the amount of model data that has gone into computing this humidity, because as both was discussed yesterday, and I think Sean also mentioned it, these dry reflectivity, bending angle, reflectivity, dry variables, those variables are very close to pure observations. Humidity, there we need some additional information from model to be able to separate the influences on the refractive index from humidity and temperature. So this a priori fraction here to the right is a sort of quantification of that impact from the model. And as we can see, there is so bluish here is almost pure model. And as we can see, there is the highest, the largest observational information is let's say low and mid latitudes between 2 and perhaps 8 kilometers or so. Yes, so that was humidity. Then we compute time series of monthly mean data. This is an example of temperatures at the equator, and we see some of the phenomena here are, for example, we see the QBO quite nicely. So this is a almost 20-year time series. We see the QBO here in stratosphere. We also see the tropopause very clearly, and we see in the troposphere we see that the temperature variations, the interannual temperature variations at least, are very strongly dominated by El Nino, by ENSO. In the bottom plots here we show an ENSO, one of the ENSO indices. And there's a strong correspondence here between heating of the troposphere and the positive phase of ENSO. And we see the same if we look at things like global humidity, for example. It's also very strongly influenced by ENSO. So that was low latitude time series. Then we have an interesting piece of work which perhaps was mentioned by Sean, I don't know, but because our colleagues at ECMWF, Sean Healy et al., they actually took our geopotential fields from RO data, and we're able to show that we can actually derive the mean zonal winds at the equator from these geopotential fields. So it's been known before that we can, by using the geostrophic balance outside of the equator, we compute winds from the geopotential fields, but they show that we can actually do this also at the equator. So QBO, the QBO wind variations are actually sort of encoded into the geopotential fields that we observe. We can also look at time series at high latitudes. These are, let's see here, these are temperatures, high northern latitudes. So to the left here, we have anomalies relative to long-term means, dominated by seasonal cycle. In the middle, if you remove the seasonal cycle, the time series is dominated by polar vortex buildup and breakdown and sudden stratospheric warmings, and that is what is shown to the right here. So this was a case with very cold conditions in the polar stratosphere, and then a sudden breakdown of the polar vortex and a sudden stratospheric warming, and then build up again by polar vortex. And these things can be, we can actually follow the evolution of these of the polar stratosphere. This is a comparison of RO with MSU temperatures. It just shows that there is actually, if we just downsample sort of the RO data. The RO data has a much higher vertical resolution than MSU data. If we sort of compute the MSU brightness temperature corresponding to from RO data, we can show that there is a very good correspondence there between the two data sets. Then, since we now have 20 years of data, we have been able to actually contribute to the latest IPCC report. So this is an example of tropical and global trend profiles that we compute from RO data, which are the bluish lines here. RO data from 3 centers, from ROMSAF, from Wegener Center, and also from UCAR, and compared to radiosondes, mainly radiosondes and ERA5. And as we can see, there is a certain discrepancy, particularly in the upper part of the tropical tropopause, upper tropical troposphere, where we can make use of these higher vertical resolution of our data. And this is also another plot that were shown in the IPCC report, showing the observed trends to the left here, decadal trends, degrees per decade, latitude versus height, and here we have 2 projected long-term trends under 2 different scenarios. And as we can see, there's not too dissimilar. So we can actually begin to observe what the full trend distribution that we get from the climate models. Here's another example of work that we did about 15 years ago. Mark Ringer and Sean Healy published a paper saying that bending angle trends would work excellent to use them to detect trends in the global stratosphere. And they said at that time, about 15 years ago, they said, well, towards the after about 11 10 or about 11 to 16 years, they predicted it would be possible to actually detect trends. And what we've done, so to the left here, we have the trends that they showed in that paper, and to the right here, we have the trends that we now can observe. And as we can see, in at least in low and mid latitudes, there's a great deal of correspondence between these two plots. So we can actually quite well confirm what they predicted almost 15 years ago. Slightly lower correspondence at high latitudes, but which is to be expected because the variability there is much larger. So yes, and a few other examples here of comparisons between our data and models done by Mark Ringer at Hadley Center using data from NASA, JPL. Here looking at just annual mean geopotential height distributions, and here looking at the amplitude of the seasonal cycle. And finally, let's see if I have time left. Yes, perhaps a minute. So here's an interesting example of, as I said, using not only data from sun synchronous orbit, but from many missions that observes at all diurnal cycles. We can actually observe the thermal tides in the atmosphere. The things called the tide that moves with the sun is called migrating diurnal tides, and it's a bit interesting because it has. I did a work here together with Stephen Leroy to try to fit. He has developed a method where we can fit spherical harmonic data, global spherical harmonic data to RO data, and now he added a component where we can also fit sinus basis functions to the in local time to these data. So we can study how the state looks at different local times, the global state at different local times. And doing this, we can actually identify different components of these migrating diurnal tides. We can identify vertically propagating wave and a vertically trapped oscillation, which is a bit interesting because this has implications for models. It has to do with how energy is being dissipated at the top of the stratosphere and things like that. So that's also an interesting application that has just started to be explored. All right, so to conclude, then we have nearly 20 years of our data available for generational climate data records here, and EPS-SG will continue to provide our data well into the 2040s. And as I've tried to emphasize here, we should see EPS-SG as a very important component of the global RO observing system, but other data are also important as well to fill in gaps, for example, in the observation of diurnal cycle. And our data provided it's a very long-term stable remote sensing data with a global coverage. So which means that we are able to provide these long time series. It's important for climate reanalysis. It's also important for just monitoring the climate, the rate of warming of the atmosphere, and to be able to contribute to IPCC assessments and things like that. There are a range of applications, also many I didn't mention here. So we have these stratospheric winds, polar stratosphere, diurnal tides, static stability and gravity waves. I didn't mention that. And I should just conclude by saying that there is a firm commitment from EUMETSAT ROMSAF to make these RO-based climate data records available. and they will be made available, including regular updates at quite frequent occasions. Yes, okay, so I think I stop there.
Thanks, Hans.
Should I stop share?
It's a good talk. I will just bring up the questions for you.
If I can see them.
I have to share the screen still. Can you see them actually? When does the can you see that, Hans? Yeah. When does the ROMSAF climate data date back to?
Okay, so the METOP data started in 2006, but we do reprocessings, and we plan to do this at regular intervals, perhaps every 2 to 3 years. We will do an update, to include recent developments in the processing, but we start with CHAMP data from the end of 2001. So our time series starts in the end of 2001 and then goes forward.
Okay, thank you. Take the next question. When humidity, temperature, etc. is retrieved, taking into account the model variables, does the model already has the assimilated RO data?
It has, but in order to avoid circularities, these kind of sort of problems, we use forecast data. So at a certain point in time, the actual RO data that we work at that point have not been used in the model data. Other RO data have been used, but not that particular set of model data. So we try to avoid these circularities to the as good as we can so by using these forecasts rather than just analysis fields.
Yeah, nice explanation, Hans. Thank you. Go to the next one. Why do the bending angle trends converge?
Well, the plot that I showed there is it showed the trends as a function of the length of the time series. So simply, if you have an atmosphere with a certain variability, if you start with just 5 years time series and compute trends, and then compute the same trend at 6 years, at 7 years, at 8 years, and so on, you will start with, in beginning of this time series, you will have the trend will be variable because of the atmospheric variability. But as the time series gets longer, the trends stabilize. And they stabilize. If you look at this, if you go from, let's say, 5-year time series to 20-year time series, we can see that they stabilize at almost the after the time frame that Ringer and Healy predicted 15 years ago, slightly bit longer. They said like 16 years or so, 15, 16 years, and it's perhaps slightly longer, but 20 years should be enough to actually get a fairly good to see the atmospheric trends and to compare them with climate model.
Okay, thank you. I think that's all the questions for you. We will take a short break now, and we meet at 15:15 Central European time. But yeah, as Regina has put in the chat, we are also interested to hear feedback. So like yesterday, we would like to get your feedback on today's sessions as well. Thank you, Hans.
Yes, thanks.
Going for the break.
Thank you very much, Sverka. Thanks for organizing this user preparation webinar. So I am Riccardo Trapietro, and on behalf of the radio occultation team at EUMETSAT, and with the help of Manuel Hernández Pallares from the Universitat Politecnica de Catalunya, we are going to show you some application of the radio occultation data in the space weather domain. So basically, our talk is, we will start on discussing with you how we can use radio occultation data for the ionosphere and space weather monitoring. We will provide you an overview of the GRASS ionospheric extension experiment that was recently run on board the METOP-A satellite of the EPS system. We will show you the ionospheric monitoring capabilities of the new radio occultation instrument on board EPS second generation, and give some hints on the product descriptions. Finally, we will discuss some advancement and the recent results of regarding the electron density profile retrieval. But it's really my pleasure to introduce you our friend and colleague Manuel Hernández Pallares from the Universitat Politecnica de Catalunya. I have to say that he is one of the most prominent experts on ionosphere and space weather monitoring, in particular when the monitoring is performed using GNSS signals from ground-based and satellite-based receivers. So please, Manuel, you can start.
Thank you very much for your kind invitations and for your kind words. Okay, so yes, the radio occultation GNSS observations, as it has been shown in previous talks, are typically obtained in observations from LEO, from low Earth orbiting receivers, observations below the local horizon. And this makes that them very sensitive to the vertical variability for both. For neutral reflectivity, let's say below 70 kilometers, and for ionospheric refractivity, let's say above 70 kilometers. So this makes these kind of observations very important to get high resolution vertical profiles, in particular of parameters very sensitive to space weather, like ionospheric scintillation indices and electron density. And also they are also very valuable to be ingested in simulation models combined with other kind of observations, or either using background ionospheric models. So in the next slide, you can see a layout and an example obtained from Jakowski et al. 2007 paper. And this layout summarized that, let's say, that we are lucky, let's say, for the ionospheric sounding, for the electron density retrieval in radio occultation scenarios using multi-frequency GNSS observations, because we don't need bending. This can be done using carrier phase data only, expressed in terms of the line of sight contribution of different layers, and estimating simultaneously the, for instance, this can be done the ambiguity, carrier phase ambiguity, thanks to the chain of geometry. So this makes the things very simple. Of course, for instance, under an external assumption, in principle, which is the spherical symmetry, then we can apply a sort of Pilonian strategy from the top to the bottom. Let's say the Abel inversion, it's called the Abel inversion. And this allows to get also realistic electron density profiles. But in the next slide, we can see that also this simple approach can be maintained, taking into account the horizontal gradients as we introduced in 2000, using the concept of separability. So splitting the electron density as a product of the unknown shape function and the BTEC, which is the vertical total electron content, which is provided, for instance, by global ionospheric maps. In this way, we improve the results and we keep the simplicity, and also only using carrier phase data. Of course, we are assuming a straight line. The straight line has an error, typically below 1 kilometer. In extreme cases, slightly more than 1 kilometer. So this is much smaller than the typical variation scales variation scale of the electron density in the ionosphere. So it's very fine assumption. In next slide, we can consider one of the applications previously mentioned regarding space weather is for scintillation. So as it was shown in Donggu 2020, the observations of the radio occultations, which are quite long, quite extend over the region, over the targeted region, can be very sensitive depending on the relative orientation of the patches, of the electron density patches. So this makes this kind of observations also a very good input for studying the vertical distribution, in particular, of the scintillation. In next slide, this is, for instance, this is a very clear example. As you can see around the solstice, June solstice, and around the December solstice, and around the September equinox, it can be seen versus height, the distribution of the scintillation. So in particular, we are considering, and it can be seen like around 100 kilometers in the A region, the situation is much more affected. I mean, due to this very narrow patch of strong electron density. In next slide, we can this can be taken profit, let's say, to study the occurrence of the sporadic layer, which is this strong features that sometimes happen associated sometimes with particle precipitation, very clear, typical space weather event. And this subject is quite hot since, for instance, the Arras et al. Paper from Gerald in 2008 until the Liu et al. Paper in 2021. So the radio occultation data is very important to provide the climatology and the occurrence of the sporadic layer, which also can have an effect as in the retrieval of the neutral refractivity profiles. Okay, so in next slide, we have an example about data simulation that we mentioned at the beginning. So we can combine radio occultation data beyond the assumptions of the Abel inversion or the improved Abel inversion with, for instance, ground data, because both have complementing properties which makes much more feasible to do global tomography. And this was also in 1998. This was the first time this was done using radio occultation data for space weather studies, following Bass and Mitchell in 2008. So this is, of course, another important application. In next slide, we can see the top side part. We have not talked about the top side part so far. We were focusing on the part of the ionosphere below the LEO height, for instance, 800 kilometers in the case, approximately in the case of the EPS second generation satellites. But what happens with the top part? So the top part, we have valuable data coming from the precise orbit determination GNSS receiver. And this data is able, combined with radio occultation or by its own, allowed to get the VTEC above the LEO. So this was shown in Prol and Hock 2020. In next slide, yeah, I return the floor to my colleague Ricardo.
Okay, thank you very much, Manuel, for this nice summary of what we can do with radio occultation. So now I'm going to talk about the ionospheric extension experiment we ran last year using the GRASS radio occultation receiver on board METOP. You might know that the GRASS receiver was developed several years ago with the focus of providing to our users very high quality neutral bending angles. So the measurement were covering up to the high 80 more or less 80 kilometer levels. But during the METOP A end-of-life technology test campaign in 2020, we were able to temporarily extend the vertical measurement range of grass into the lower ionosphere. We ran 3 different experiments, 2 of them up to 300 kilometer and 1 up to 600 kilometer. We were aware about the possible limitations and problems because we know that the antenna gain of the grass instrument was focused on the neutral part only. So we expect some problems in tracking the signal higher up. We know also that the grass has a limited number of channels available, so we were a bit worried about the possible decrease in the neutral bending angle profiles that we can provide to the user. But at the end of the day, we were able to generate dual frequency, high rate bending angles on both bending angles and ionospheric amplitude and phase scintillation indexes with grass without impacting too much the neutral atmospheric occultation data provision to our user. We noticed that with the experiment up to 300 kilometer, we had something like less than 1% of less occultations provided to the users. Thanks of this, EUMETSAT decided to extend these capabilities of grass also to the grass instruments on board METOP B and METOP C, and probably this will be made operational early next year. Anyway, this is an example of ionospheric occultation. Here is in terms of signal to noise ratio for L1 and for L2 in function of height. You can see that the maximum of the signal to noise ratio is in the neutral atmospheric part. But then we can measure really nice signal fluctuations here. But then you can see that the signal to noise ratio starts to decrease because of the limitation of the antenna pattern. Despite of this, we were able to provide bending angle profiles on dual frequency, on both frequency, up to 600 kilometers, and also scintillations profile at a high rate, 50 Hertz in this case. This is an example of amplitude scintillation on L1. You can see these nice scintillations which are due to these signal fluctuations on L1. But then the scintillation profile is quite flat up to 350 kilometer, and we are sure that we can provide scintillations over this area. But then the scintillation profile starts to increase with height. And this is for sure not due to ionospheric activity, but is due to the increase of the noise in the signal, and therefore because the gain of the antenna is going down. Anyway, I would like to show you these nice results we obtained by our analysis. So here is we reported the time series of the zonal mean of the S4 on L1, recorded by grass between 90 and 110 kilometer. You can see here that the scintillations are in this layer are mostly varying during the times. So here is 1 month more or less. Are more higher in the day with respect to the night, and are higher in the June-July experiment with respect to the September experiment. So this is more or less, this is in line with what Manuel was showing before, because we think that these are due to the occurrence of the sporadic layer, which for the summer period is mostly occurring or affecting the northern hemisphere, and mostly on the day with respect to the night. I can now go to describe you the radio occultation monitoring capabilities on board EPS second generation. So yesterday I have detailed, let me say, what will be the radio occultation tracking capabilities. But just to remind you, the radio occultation instrument will track multi-GNSS constellations signals. It will track both data and pilot component on L1 and L5 from GPS, Galileo, and Beidou. The receiver has a limited number of channels, of course, but we have 8 channels available for each entire occultation. The focus will be also for EPS second generation, the neutral atmospheric part. But at the end, we have at least 4 channels made available for the ionospheric occultation in L1 and in L5. This means that if by tracking only the pilot component in closed loop, we can provide to the user 2 risings and 2 settings ionospheric occultation contemporaneously. And these occultations are going up to 500 kilometers. This is a limit imposed by the antenna of the radio occultation receiver. And we have to say that at 500 kilometers, the electron density is not really negligible. And some care must be kept in the retrieval algorithm for the electron density profile, because it should be initialized somehow. Anyway, HESA is now, we asked HESA to try to understand if we can extend higher up this limit, possibly up to 600 kilometers. And the analysis is going on. Anyway, yesterday I also described you the details about the products we are going to generate, and the ionospheric data will be included in our level 1B product. It will be one netcdf file for each occultation. There are a lot of information inside our netcdf file. Please refer for the neutral part to the yesterday presentation. But I would like to highlight you here the role of the low-level measurements in the level 1A subgroup, because this is really important also for ionospheric monitoring. We are reporting in this level 1A subgroup the low-level measurements divided by frequency. And these measurements are essentially time series of phases, signal-to-noise ratios, and pseudo ranges, as well as excess phases and excess pseudo ranges, covering at 200 or 250 Hertz the neutral part and the ionospheric part. We are providing also the LEO and GNSS positions and velocities, which are already interpolated for the measurement timestamps. We are providing the signal, the arrival, the azimuth and elevation angles of the arrival signals, which are quite important also for the ionospheric monitoring. The ionospheric data are included in the ionosphere subgroup. This group includes all the profiles in ionosphere we are able to generate. The profiles are included in the TINED and high resolution groups. The content of this group is the same, apart of for the vertical resolution of the profiles, which will be 100 meters for the high resolution data and 1 kilometer for the TINED data. But the two groups contain basically arrays of L1 and L5 bending angles, impact parameters, and impact heights, L1 and L5 phase and amplitude scintillation indexes, as well as geolocation parameters for each point in the profile. We have also an occultation subgroup where we store the georeferencing information for the ionospheric occultation. Level 2 ionospheric products will be provided by the ROMSAF, the Radio Occultation Meteorology Satellite Application Facility. In near real time, they are going to provide electron density profiles starting from 100 kilometers to the orbit altitude. And they are also going to provide the scintillation indexes profiles using different techniques. I want now to highlight the point that electron density profiles will be provided up to the orbit altitude, not only up to 500 kilometers where the measurements will stop. And this is quite a tricky task. And we have developed some algorithms for this. And I wish to ask Manuel to introduce the first of these algorithms.
Thank you very much, Ricardo. So, yes, the scenario is very challenging, as it was commented by Ricardo, because we have the LEO flying at around 800, and we have to wait until 500 kilometers to get observations down. So this is the bad news, but the good news, or the challenging news, but the good news is that in 2016, Germán Olivares Pulido et al. Shown that the top side of the electron density profiles follows very well a Chapman model with a linearly increasing skull height, following a particular case of a more general model developed in 2012 by Sumei. So this was the first time demonstrated from the cosmic radio occultations. So this provides us a sort of a skeleton to fill the gap of this blind region of 300 kilometers from 800 to 500. So this is important to emphasize that this is true for top side. Bottom side is much different, but it's in top side where we have the problem. So in next slide, we provide a first application of this finding in 2018 in a paper where we show that the extrapolation works very well using the linear Barichat model. If you know very well before the bottom part, below 500 kilometers of the electron density profile. In the next slide, in the Haishaliu et al. 2019, summarize the new hybrid method. Hybrid method solving together the double inversion and the skull height at the 4 parameters for the linearly increased skull height model. This is the FHIRO. Now there is another more simple method, CIRO, faster. Now we are working on the second version of FHIRO, much faster than the first version, and fixing the transition effect affecting some radio occultations around 500 kilometers. Thank you. I return the floor to Ricardo.
Okay, thanks, Manuel. And most recently also regarding this problem we have in extrapolating the electron density profile, Sean Ely and Ian Culverwell developed a recent, I don't know why there is, okay. Huh? Okay. More recently, Sean Ely and Ian Culverwell provide a new approach based on a one-dimensional variational retrieval method for derive the electron density profile. In this approach, the truncated, so the radio occultation measurements up to 500 kilometers are counted part of the forward operator H, which maps the electron density profile to a particular observation space, like what Sean told before. The observation space for the ionosphere is the difference between the bending angle at the two frequencies. This is somehow different from what is already done by other centers, where the electron density profile, as Manuel introduced before, are computed using carrier phase information. But the carrier phase information should be leveled to the pseudo ranges to have absolute values, and then the pseudo ranges suffers of the differential code bias. So some bias is always playing around the retrieval of the electron density. In this case, using bending angle, these are not suffering of this bias. Another assumption is made because the electron density profile should be modeled as a sum of one or two or several one-dimensional Chapman layers. Each Chapman layers is modeled by 4 parameters, which defines the state vector here of the forward operator. These 4 parameters for each Chapman layer are the electron density peak and its height, the scale height, and its gradient, vertical gradient. The main aim of the retrieval approach is to minimize, as Sean has already shown for the neutral part, to minimize this cost function in a statistical optimal way in order to combine the a priori information included in the state vector, here the Chapman layers parameters, to fit the observations that in our case is the difference between the bending angles. The 1D-var adjusts these Chapman layers parameters to do the fitting after a few iterations. Here is a nice example that Sean and Ian showed us regarding one grass occultation observed during this extension experiment. The results are here shown in terms of electron density profile and on the observation space profile, which is the difference of L2 and L1 bending angles, L2 because we are talking about grass. So you can see here if the model is fitted, if the observations are fitted with one single Chapman layer model. Once it is forward propagator, here is the background. Okay, we can see that the 1D-var tries to follow the observations here in green reported in this plot. The final result is the blue line. So we can see that once the bending angle difference is assimilated starting from 200 kilometers, the fit is really good with the fit with the observations. So this is the result of the 1D-var. After this, we know that the 4 parameters of the Chapman layer that can be used to infer the electron density profile here shown. But if you can see here, we have more than one layer. So Sean and Ian tried to fit the observation space using a double Chapman layer. Okay, so you can see the differences by using two Chapman layers. You can see that the fit with the observations is much better till 120 kilometers higher up, where the bending angle are assimilated. Again, the 8 parameters in this case of the 2 Chapman layers can be used to deduce the electron density profile. So here is these results are just published. This is a really interesting results, and we are looking forward to these kind of approach also in the future. By the way, this will be included in the next radio occultation ROPP software that was described yesterday by Ian. So I can go to the summary. We presented why the radio occultation observation can be important for ionospheric and space weather applications. I show you some the capabilities of the radio occultation instrument on board EPS and EPS second generation. Something about the product, and we discuss, we provided you the current developments on the electron density product extension to the LEO orbit for the truncated radio occultation we expect to have in EPS second generation. So this is all. Thank you very much for your attention. Thanks, Manuel, for helping me describing this.
That was a good double act, Manuel and Ricardo. You managed very well, actually.
Thank you very much.
As good as Sean and Axel. So you all are very good.
I will, sorry to interrupt you very briefly, sorry. It's a small clarification, if you never mind. It's regarding that the models using carrier phase data doesn't need the pseudo range. So it can solve electron density without using pseudo range and without using the CVs, just the correlating the ambiguity due to the change of geometry. Just a small comment. Yeah. Thank you.
Okay.
Okay.
Yeah, everyone, please, you can post your questions still. We are here. Let me just bring up the slide, okay? The questions. Can you see them?
Not yet. Yes.
Yeah, the first question, does the ionosphere change over the years, and can we detect this from the refractivity?
Manuel, you are the expert. You can go ahead.
Okay, thank you. Yes, for sure. I mean, also from the very simple integrated refractivity, let's say, vertically from the VTEC, you can see very clearly the different modes, the different periods that appears associated to solar cycle, semi-annual period, seasonal period, and either the solar rotation period. So yeah, it's very clear.
Mm-hmm. Okay. I don't know. So we can also answer to the second question here. I can see.
Yes, sorry.
Which parameter?
Sorry, I was distracted for a minute. Sorry about that. I just approved that question and I bring up the next one. Which parameters other than TC can be derived from RO in the ionosphere? Proton flux, geomagnetic field?
No.
For
sure, electron density.
Yes. Indirectly, you can detect indirectly, but this is not the frequent usage. When there is a solar flare, there is, but you have to. It's very difficult because the radio occultation is a very fast event, but the solar flare gives a footprint at the F2 layer around the peak, which is very fast and is proportional to the UV flux rate increase. And so, but yes, Ricardo said it's typically the electron density. The geomagnetic field is, this should be something related with Faraday rotation or second order ionospheric turn. and you will need we will need much lower frequencies, not the frequencies of GNSS to get a clear signal there. Yeah.
Okay. Thank you. In yesterday's talk, you mentioned that for EPS-SG RO ionosphere products available up to 300 kilometers is based on the GRASS experiment, which showed noise about 300 kilometers.
No. The method of second generation, the radio occultation instrument will provide ionospheric products up to 500 kilometers, possibly, probably up to 600. So the GRASS experiment was really something that we were looking forward, because just to see if our RO instrument could have good measurements from the ionosphere, and also because we needed to prepare the algorithms for the radio occultation second generation. But the method EPS-SG will provide the data up to 500 kilometers for sure.
So is the GRASS experiment still ongoing, or?
The GRASS experiment was for 3 months in 2020, okay. But now all the other GRASS instruments on board, Method B and Method C, as well for Method A, but it will be decommissioned soon, will provide the data up to 300 kilometers. This will start early next year, probably, operationally.
Okay.
With reference
Ricardo, with reference to slide number 16, you could see disturbances using RO. Can you talk of finding TIDs using RO observations? Thanks.
I can think yes. But for the time being, we noted that presence of sporadic layers. Also, TID can be derived from radio occultation observations. We simply didn't have time to do this.
Okay. The next question, I think we still have time to take them. The scintillation on level 1 is plotted at the coordinate of impact point or LEO or somewhere else. How was the IPP? How the IPP was calculated?
So first, the scintillation on the first frequency that I've shown, I can give you again.
Sure. You want to bring up the slide?
If I have, I guess is you are mentioning something. Wait. This one, no? This one are made in terms of SLTA of the instrument. So the straight line tangent altitude, which is the height of the straight line connecting the 2 satellites, which is more or less, since the bending is not so big, it is more or less the impact height. Okay, but we are looking at the limb sounding, so there is no IPP, ionospheric pierce point definition for a limb sounding. So each scintillation value is georeferenced to the height of this straight line connecting the 2 satellites.
Okay.
Okay.
I hope I can bring it back.
Yeah.
Yes. Yeah. To manual, so we can get the electron density below 500 kilometer from RO ops, and then we use Verichap model to get the entire profile. That's asked by someone in the chat.
Yes. Well, this idea can be applied, and in fact, we applied in one of the approaches, but should be done iteratively, because the first, if you are or you can use a background model. We prefer always to avoid background models as much as possible. So if you don't have a background model at the beginning, your electron density, the first estimation below 500 will be very affected by the missing electron density that you are not properly taking into account from 500 up and above. So you need to iterate to get a topside part of the electron density profile with a reliable slope, in such a way that you can get a reliable skull height gradient, vertical gradient, and skull height 0 value at the peak. So summarizing, yes, this is one way to proceed, but iterating and with some details which are important, because you have a narrow margin. Sometimes the peak, the height of the F2 peak is too high, especially at low latitude, in anomaly, for instance, and you can have in a small room to extrapolate the linear Verichap model. This can be done, but yeah, the idea is good. Iterating is the only point.
Okay, thank you. Thank you, Manuel.
Welcome.
Those were all the questions for today. And to everyone, I would encourage you to give us some feedback in the Slido. Regina, if you can post the link to the Slido. My camera is off. Yeah, thanks. Yeah. Hello. Yeah, Regina, if you can put that poll question one more poll link, it will be good. And we are coming to the end. Yeah, so I think it's a good idea if we all show our videos. I don't think we will explode. So it will be good. Again, today's speakers and yesterday's speakers, and also some of us didn't speak on both days. Kent and Stefan and Regina, you can also show, because they had not talked, but they were behind supporting us, the speakers, supporting me and also the speakers. So hi everyone. Ian cannot show. I think he has some difficulty in showing his video, but yeah, thanks everyone. It was a great show. Thank you very much. And thank you, the participants from, oh, Ian, we can see you. Yes, so that's great.
Okay.
Yeah, so until we meet for the next webinar. Until we meet next, bye-bye. Thank you.
Bye-bye. Thank you very much.
Thank you very much for organizing.
Bye-bye.
Ciao.
It was my pleasure.
Thanks.
You're welcome.